Okay, let's also briefly talk about what happens if your solution, your displacement or temperature, is not just a function of t, but also a function of x. So imagine if you have a bar and we took a hammer and we hit it on one end, you get a stress wave that goes down it. Or maybe you have a bar at initial conditions of ambient temperature, you put a match on one end, and now we have this wave that starts moving down. You get these spatial gradients. In that case, we can introduce a finite element form. So this matrix M here is based on your finite element weak form. After you go through and integrate the interpolation functions, these are vectors based on velocity and displacement, or temperature rate and temperature. Here's your K matrix, again based on integration of interpolation functions and your forcing function. So for Crank-Nicholson, what we do is we take this rate here based on the difference in two time steps of your solution over delta t. The 1/2 is due to alpha equals 1/2, and here's the two time steps. Here's your forcing function. This is solved exactly the same way as the scalar problem. So we just solve for this vector at the future time step I plus 1. Now for hyperbolic equations, you have this acceleration term, right? So one way is we introduce this Taylor series, as we talked about in the past. Here's the velocity, acceleration at s plus alpha. And there's some discussion on how do you determine stability when you have alpha and this gamma. This gamma shown here. So if you look in our textbook, this equation gives you more detail. And so here's my delta t. It's got to be less than this t critical, which is based again on your maximum natural frequency and a difference in this alpha and gamma all over, or to the power of negative 1/2. Alright, and this is valid for a conserved system where there's no damping. So you have this type form eigenvalue problem. So let's talk about an example. This is particularly looking at a 1 degree of freedom lump parameter model, so I'm going to limit this to no spatial variation, but it'll show you how you can simplify this down into a system of equations. So here's your mass, damping, stiffness terms. We're going to rewrite this problem in terms of your displacement velocity as x1, x2. So you can rewrite this one OD into a set of first and second order ODEs of this form. Now you've got a system of equations, so instead of solving one equation, you have these two equations, but same physics. So we can put this in a matrix form. This vector is just x1, x2. Your A matrix looks like this. Here's your B matrix. Here's the state space form you may have seen in classes such as controls or dynamics. And then we can discretize it. So here you can discretize this in time using Crank-Nicholson, similar to the parabolic equation, except here you have harmonics.